for inviting me on this panel. Today, I'm going to do a short presentation to talk about the actual projects we deployed in the UK. Two projects, two examples. You can see already a photo of quite a large project in the megawatt scale, offering grid services to the national grid of the UK. Before I do that, I'm going to introduce to you the product, because it is essential to have a very versatile product to be able to deploy large-scale flow battery facilities like the ones we are deploying right now. Then I'll show you a typical CNI project for the local water authority here, and the Energy Super Hub Oxford, the ESO project, which is the one you can see here, a rendering. This CAD rendering, by the way, was done 3 years ago at the beginning of the project, and you can see here it looks like exactly what we had planned to do. First of all, the product heritage. We created Invinity a couple of years ago based on two existing companies. One was in the UK making large containerized batteries. The other one was doing a battery module. We found that to achieve the cost targets that we want and the flexibility in manufacturing with a repeatable industrial scale product, we needed to go with the module that is a very repeatable product. But for large scale deployment, we needed a containerized size system that allows us to do large plants in a short time. And we merged these two ways of thinking into what you can see here. It's 6 modules, all standard, all identical, all filled with electrolyte into a 20-foot container format frame, which is qualified as a 20-foot container and can be shipped across the oceans and by road, into this battery pack of 55 kilowatt, 220 kilowatt hour, so nominal 4-hour distance, but it can deploy up to 78 kilowatt of power. So we can push it in what we call overdrive. And that's very useful, you'll see later in the presentation, for doing frequency services where power is paramount. And that's, again, renderings that we did at the beginning. And you can see the product on the photos. It looks exactly like this, of course. And that's the Invinity VS3 battery pack. Like I said, 55 kilowatt, 220 kilowatt hours, 4-hour system, 78 kilowatt in max power, 20-foot container, 3 connections just at the front there with these 2 boxes you can see, DC, AC, for the auxiliaries, running pumps and controls, and the controls themselves, CAN bus between the modules, but then there is a proper COM system above it to interface with the EMS of the customer. It's a modular design. The 6 modules are totally autonomous VRFBs. Each of them has their own BMC. They manage their tanks, their stacks, current voltage, SOC. Everything is managed inside the module. They're autonomous. You lose one module, the other 5 continue operating. And of course, on the large scale, we have hundreds of modules. That gives this modular design is essential to make sure that the client gets continuity of service. This is the factory where they're produced in Suzhou, in China. The frames are also procured locally in China. You can see the guys fitting a module in a frame, like there was a first pre-fitting, and that one in the picture is the very first one we did. We did more than 100 since then. These are our factories in the UK and Canada. Actually, if you don't know which is which, you could see the factories look exactly the same with a big overhead crane, able to manipulate those 20-foot containers. Remember, they're full of electrolyte, so it's 25 tons. and they can be transported on the back of a truck, as you can see on the picture here, and yet there will be more picture later on. What we do in these factories, we do the stacks. The stacks are always made in Invinity's own factories in order to ensure that we control the quality and we control the performance of the stacks. And of course, the batteries themselves are FAT'd. This is that picture here, where you can see the test team doing the final FAT of the batteries before leaving the factory. And you'll see later in the presentation, it's essential if you deploy a large system, megawatt scale, like we're doing, you need to be sure that what is delivered to site is working perfectly. With this container, which is our building block, we are able to deliver small projects. You can see one container with an inverter, so the 55 kilowatt, 120 kilowatt hour. Then we can duplicate that by putting them in parallel, several containers against several inverters. And that's the project of Scottish Water is an example of that. Or we do big clusters, several containers like 9, 7, a lot of containers going into a big inverter, a megawatt or multi-MVA scale inverter. And that's the project here. So we also have a variant of that where we do direct DC coupling to PV. I'm not showing this project today, but I can share that we have 2 projects, one in Canada, one in Australia, 2 megawatt, 8 megawatt hours, each of them, very similar designs that are coupled directly in DC with the PV farm that is co-located with them. So the idea there is that with this building block, we can make small and large projects, but the product remains always the same. And that's where the cost advantage comes in series production. It's always the same product. Well, let's go and have a closer look to this project at for Scottish Water. So you can see a picture of the Scottish hills there, very far away from China. And they have PV on site. They have 4 containers. So 4 times 55, that's 220 kilowatts and 880 kilowatt hours. So almost a megawatt hour, not quite, but that's sufficient because what they do with this, they operate a water waste treatment plant, which is very much energy hungry. And the idea is then to avoid importing any electricity from the grid, and of course save on the energy bills of the plant. There's no concern really about resilience. The grid is pretty stable in the UK, but it's really about cost, and that's a typical CNI application. Offset the grid by using your PV and storage to always operate the plant independent from the grid. What challenges? Well, that was always the three types of challenges. You've got the first, deploying the machine on site, access, safety, everything. You have to control multiple containers with multiple inverters, which poses a number of challenges in terms of power electronics, in terms of controls. And we also wanted to have visibility of all our batteries every time that, at any time in the day. So we did the first deployment of our data acquisition system. Every single module, be it 1 or 6-pack with 6 modules inside, or hundreds like we have on the megawatt scale project, we can see what it's doing. We can see the temperature of its electrolyte. We can see its current voltage, power coming in, out. We see everything, and we log this data. in a big database, in a history. For what was the reason for Scottish Water to come to us? Well, it's a critical infrastructure. So a battery, like a lithium battery that would have a few years life, they're not interested in it. They want something that lasts 25 years. It's an infrastructure. And it has to be safe. So that was their two main arguments to go for vanadium flow batteries. Simple architecture. You can see two clusters, two containers each, two inverters, all in parallel. They can be operated independently, and they use them day in, day out like this. That's how the batteries arrive on site. Simply, they're already full of electrolyte. They're transported, ready. You know, we used to say plug and play. It's not exactly that, but that's the idea. They come, we connect them to the site layout, and you're in business. You can start charging, discharging. So that's how it's done with a crane. Put them in, and that's the result. We have this dashboard. That's what I was talking about. We can see what the battery is doing all the time. You can see that since they started operation in May 2022, 125 kilowatt-hour were exported. Safety, reliability, you know, all the challenges that I talked about, EMS integration, we have fixed that. And that's a snapshot from, again, our data monitoring system. We can pull all the graphs we want with it, or what it's been doing. So in green, it's power. In blue, it's state of charge. And they're using it every day of the week, not during the weekend. We see the lapse of the weekend. Up, down, you know, charge, discharge at the time that suits them for saving money. Now let's go megawatt scale. Well, that's what it looks like. Next to it, there is a big lithium plant, and this is the vanadium plant. Again, that's a rendering that was done 4 years ago at the inception of the project. And that's the system being built. You can see there's only one row there at that point in time. And eventually we have 2 rows of these containers lined up for 27 containers. So that's the project plan. You can see here a layout. So 2 stacked container, 1, 2, 3, 4, 5, all the way to 27. And the 28th container contains the PCSs, the inverters. What were the challenge? What were the technical point projects? So 1.2 megawatt, 5 megawatt hours. It can do overdrive to 2 megawatt using the function I was saying before. It's hybrid. There is a 50 megawatt hour lithium battery next to it. And the whole idea there really is to, because the flow battery doesn't degrade and is immune to cycling, the flow battery is going to take all the little cycles, especially in frequency response or when they're trading. They're going to save cycles on the lithium battery. And that's really the idea of this hybrid system. Take advantage of the flow battery to kind of protect the lithium battery. Well, paradoxical, lithium tends to be seen as our competitor. And in this sort of system, we're protecting them. But actually, I don't see it like this. There's a place for everyone, and there is a use case for everyone. And our use case is there. Long duration, safety, and we can do this. Now, what is important to note there is that they were looking a lot at frequency services. So in the UK, we got frequency response, dynamic moderation, dynamic containment, dynamic regulation. The DM, DC, DRs are very fast services, and you'll see in a minute why I'm saying that. That's the plant. You see, simple architecture, 1 big inverter, one P transformer, 3 big inverters there, with each of them a cluster. In a cluster, you've got 27, you've got 9 containers, so 3 clusters that's 27. You've got 54 modules, 9 times 6 each of the clusters, and they're stacked on top of each other, as you could see on the pictures. This is what it looks like when it's finished. This is another view where you see that's big. We're talking about megawatt hour scale. That's what it looks like. And that's small. We have projects now that we're working on that are, this is 5. We've got projects in 8, 10 megawatt hours in motion already in delivery phase. But what did we learn at ESO? That was the first time we were doing something that big, 5 megawatt hour, 27 containers, 162 modules, 54 single modules attached to a single inverter. And we resolved all the controls issues, all the challenges with, maintaining a stable DC bus with that large number of modules. We achieved the 2 megawatt overdrive, and most importantly, we qualified beyond all expectations. We had expected 1.5 seconds response time for frequency services. We ended up at below half a second, which qualifies us for the faster services, which are the most lucrative in the UK. And that's it. There's always a misconception about flow batteries that they're slow, they have to run pumps. This is not true. Everyone in the room, I'm sure, knows that. It's just electrons flowing. The inverter moves his voltage up or down on DC bus, and laws of physics, electrons, they come in or out, and that's instant. Actually, the 5 megawatt hours is the power electronics. The 500 milliseconds is the power electronics speed. That's in the control speed. That's all it means. It's not the vanadium ions or the vanadium electrochemistry that has any play in it. It's instant. So flow battery, for those who don't know yet, is fast. It's really fast. It can do all the services that are currently in play. Again, that is that same battery at 2 megawatt, in blue, the power scale, in red, the SOC, state of charge, and you can see that trading 2 megawatt up, down every day. My conclusions was quite simple. Vanadium works. Vanadium electrochemistry does what it says. That's what we have always said for decades, that electrons come in and out, and it has the performance. We delivered the performance that was expected from these batteries in real conditions, connected to a commercial energy management system, to the national grid, or in a water treatment plant in harsh conditions. It works. They can do all the services. We talked about response time and reliability. They cycle day in, day out like any other asset. But how to, they're safe, of course. They have the durability, which qualifies them for infrastructure. And how we achieve that is by having a product-driven approach with manufacturing, QA, processes, bringing VFBs into industrial scale. We're not in prototype with land anymore. We're not in the lab, of course. We left the lab a long time ago, but not that long ago, actually. We're not in prototype. We're not in field prototype. We are there in industrial scale. That's where we're entering now. And the approach, there might be others, but is a containerized, ready-to-go standard battery, pre-filled in factory, factory acceptance tested. And that's crucial for large deployments because you don't have a lot of weeks to deploy such a megawatt scale system, and you want to arrive on site with batteries that require the minimum installation and commissioning time. So that's our approach, and that's my presentation. Thank you very much. I have questions now, if there are any.
All right. Any questions for Jean-Louis? We have one right here.
Hello, Mr. Jean-Louis. Yeah. Before my question, could you do me a personal favor to send my best regards to your CTO, Andy Claassen? He's my best coach in engineering. Yeah.
I'm glad to hear that. I'm talking to Andy almost every day. I'm talking to him tonight.
Yeah, tell him his old friend Desmond miss him very much. And the day spent with him is my most valuable experience for engineering. Yeah. So my question is that your power module is 110 kilowatt. Why did you make it big? Why don't you make it bigger? Like 220? It saves containers and seems more simpler in electrical and pipelines. So in what kind of consider you make you set your module like 110 kilowatt? That's my question.
So, so the module, the container itself is 55 kilowatt. It's capable of going up to 78 in DC. Actually, the 220 kilowatt hours are the driver. And that's basically what fits into a 20-foot container, both in terms of volume, but most importantly, in terms of weight. You know, 220 kilowatt hour, you do the couch, you know your watt hour per liter is around 11,000 liters of electrolyte in there, and you multiply that with the density of our electrolyte 1.4, you get to the 25 tons with all the ancillaries around, you know. So that's the driver. You want to have a transportable, ready-to-go container full of electrolyte, and that's 220 kilowatt hour. And then it's just a 4-hour system. So 220 divided by 4, 55 kilowatt. That's how we came up with the size.
Okay.
So why not bigger? Because you cannot transport it.
Great. Any other questions here in the room? There we go.
Mr. and Luis, thank you. My question is, we know VS3 is a 4-hour system. We have some other solutions, for example, long duration system, like 6 hours, 8 hours, or even longer. We have such kind of product or solution. Other question is, I want to know the cost based on your current project. For example, some typical projects, I want to know the on-site civil work installation cost, and finally the maintenance cost, maintenance operation cost, just in percentage. For example, the equipment cost is money, and the best part of each cost is how many percentage. Please give us some suggestion.
Right. I'm not going to share cost values, of course. If you want to know the price of our batteries, you're welcome to contact our commercial team, Matt Harper, my colleague in the commercial team, and you'll get a price. What I can say to answer your question is that the batteries themselves represent 75% to 80% of the cost of a system. Installation is, you know, less than 25% for sure. If you get a large project, it can be down less than 20%. So basically, the answer to your question is 75 to 80% of the cost of a large megawatt scale system is the batteries.
Okay. I think we have a question online.
Vicky, you can ask a question.
Yeah.
Hello, Mr. Jin. One of our concerns is that the additional protonic changing membrane is the core component of the vanadium redox flow battery. So we want to know, do you have any plan to put a Chinese manufacturer in your supply chain list in the coming years or even months? Thank you.
Are you talking about the manufacturing of the electrolyte?
upgrade your supplier of the PM, take PM for example, to
Of the memory.
specifically- Yes, that's it.
Okay. I'm not going to share where we get our active material for the stacks. I'm not at the liberty of doing that. We consider that confidential. But what I can say is that we are optimizing our supply chain, and we do have a lot of our supply chain in China. Now, as I mentioned before, the battery containers, the modules are made in China. We have electrolyte suppliers there. We are not tied up to any particular supplier. We are optimizing our supply chain. So if you have good products, be in active materials or electrolyte or anything in the battery, then please contact us, contact our supply chain, and we will evaluate.